this last part of the lecture. So what I want to tell, or what I want to reprise first, is the Gibbs-Duhem relation. This is basically, as you can see here, it is N1 d mu1. This Gibbs-Duhem relation. So mu1 is the partial molar Gibbs free energy or chemical potential of species 1, and then N2 d mu2. This is for species 2. Similarly, this is for d mu I, Ni d mu I, which is equal to 0. So basically, in more compact form, if you want to write the Gibbs-Duhem equation, it basically tells you sigma I equal to 1 to all the components, Ni d mu I equal to 0. Note that the same Gibbs-Duhem relation, basically where mu I is del G del Ni, where Tp, temperature, pressure, and Nj not equal to I are kept constant. Now let us have a so basically this extends to any partial molar property. So let us have a partial molar property Z. Then basically say Z is the total property, like G, right, Gibbs free energy. So Z is some sort of a total property of the mixture of the solution. Then Z equals to what we know, Ni Zi bar, right? That is first thing that we know. Second thing that we know from Gibbs-Duhem relation, that summation I equal to 1 to C Ni d Zi bar equal to 0, right? So these are the relations that we basically know, right? So these are the relations that we know for any property, any harmonic property Z. So if you have any harmonic property Z, then you basically can write it as Ni Zi bar, and if it is Ni Zi bar, then basically this is the Gibbs-Duhem relation, right? This is the Gibbs-Duhem condition or Gibbs-Duhem equation, right? The Gibbs-Duhem equation. And then there is also another equation, that dz equals to Ni d Zi bar. Again, as you can see, i's are repeating, so there is a summation here, right? There is a summation over I equal to 1 to C, right? So this is all we know, right? But one thing I missed in the previous lecture was the how do you basically define the concentration of solutes in a solution? Because when you prepare a solution, whether it is liquid in liquid or solid in liquid or solid in solid, there is something called in a solution. You have a solution is basically, as you know, is solute, and you have multi-components, so you can have different solutes, right? Different types of solutes, like solute 1, solute 2, solute 3. So it's a multi-component solution. So, and you have a solvent, right? Solvent and solute, right? Now when you have solute and solvent, then there are these varieties of solutions. That solution, there is a classification that we know, that's a solution can be concentrated, another is basically dilute. Dilute means the mole fraction of solute is very, very small compared to the solvent, right? Now when it is concentrated or normal solution, then basically you use mole fraction of solute. So Xi, say if I the solute, if I consider I to be a solute component, so this is solute component I. Then if you have Ni is the mole number of I, and you have total the total concentration, the total number of including solvent, the total mole number is basically summation I equal to 1 to C, because see, the components will include the solutes as well as the solvent, right? It will include the solutes as well as the solvent. So basically, so summation I equal to 1 to C in I basically includes all the solute components plus the solvent component and you can call it like something like N, and Ni by N is nothing but mole fraction Xi of the solute, right? So mole fraction Xi of the solute is one way of looking at or quantifying solute. Another way of quantifying solute is using weight fraction, right, or Wi, right, the small Wi. As you can see here, this is lowercase Wi, and lowercase Wi is the weight fraction of solute, when capital Wi is the weight of solute, I, or mass of solute I, and summation Wi, this is upper cap Wi, that is, remember, this is also, so summation upper cap Wi from I equal to 1 to C basically is nothing but the sum of all the sum of weights, or sum of weights of all the components, including the solvent and the solute components, and basically you can call it something like W. Okay, so if you have W and if you have Wi, then what you get is a lowercase Wi, which is basically weight fraction. Now weight fraction, many a times weight fraction is given as weight percent, even mole fraction is given as mole percent. So if you have mole fraction Xi, then mole percent is nothing but 100 Xi, right? Similarly 100 Wi will give you the weight percent, right? So you can have mole percent way, so we can tell that mole percent or atomic percent way, we often tell that these are this mole percent of solute in this mole percent of solute, say some solute A, and some mole percent of solute B, something like that, then mole percent is nothing but 100 times mole fraction. Similarly, weight percent is nothing but 100 times weight fraction. Now these are basically used for looking at, for defining concentrations of solutes in a normal or a concentrated solution, right, in a normal solution. So if it is not dilute, when I talk about dilute means the amount of solvent is so high that the amount of solvent is so high that in the denominator you are only considering the solvent in the denominator, because the amount of so basically you have, say for example, X1 is your solute mole fraction and X2 is your solvent mole fraction. Now X2 is something like, say for example, 0.999, and then X1 is nothing but 0.001. So in that case X2 is much greater than X1. Now in such a case we can call it, so X1 is your solvent, let us assume that X1 is your solvent. So let us assume that we have a solvent X1, solvent is component 1, and that has a mole fraction of X1 which is greater than X2. Then in that case, and so solute is 2, so this is say a binary solution, solute is 2, then X2 is so small that we don't, so basically X2 is so small that we do not consider X2 when I count. So basically if I have, for example, this corresponds to say I have, say, n moles, or n moles are total, and it which contains n1 moles of 1, right? 1 is your solvent 1, and n2 moles of 2, component 2. So component 1 is the solvent, right? Component 1 is the solvent, right? In that case X1 is n1 by n, which is roughly equal to 1, and X2 is n2 by n, which basically approaches 0, right? So in such a case we use a different measure for concentration, such as molarity. Molarity basically tells you, so molarity of solute I basically tells you the amount of the mole numbers of the total number of moles of solute I in the total volume of the solution, right? In total volume of solution or volume of solvent. You can also call it the volume of solvent, because solvent is very large. So you are basically telling that over the total volume, which includes the volume of the solvent, which is quite significantly large, you are basically trying to find out the molarity, that is the concentration or moles of solute per unit volume, moles of solute per unit volume, right? For dilute solutions, you use such a so per unit volume of the solvent, for example, right? Per unit volume of the solvent, but or per unit volume of the solution. But in the solution, as you can see, the contribution of solvent to V is enormous compared to that of solute, right? That's the dilute solution. For dilute solution, we also use something called molality, which is basically defined as mi, small mi, lowercase mi, which is Ni by weight of solvent. We basically look at the weight of solvent, and the weight of solvent is expressed in general. When I talk about molality, it is in kg, right? It is in kilogram, right? So now there is one point that we were looking at the partial. So we were looking at partial molar Gibbs free energy, right? Partial. So we called it partial molar Gibbs free energy, right? And we defined it as mu, so of component I equals to del G del Ni, that is change in the, so change in free energy, change in the total Gibbs free energy. Again, change in total Gibbs free energy, remember, with the change in the mole number of component I, keeping all other mole numbers of all other components constant. So Nj, which is not equal to I, is constant, temperature is fixed, pressure is fixed. So this is this. Now, as you know, the G, so you had these terms like U, S, V, N, right? We had this energy as a function of S, V, N. So that time, and you then had, so, and as you know, S and T are conjugate, V and P are conjugate, N and mu are conjugate. So basically, think of these conjugates, ST and VP. So what we talked about is like H. H is basically, we told, this is for a pressure reservoir. When we use enthalpy, then we write S. H is a function of S, but V is replaced by its conjugate, which is P. Similarly, because in this case we are telling that the system is in contact with a pressure reservoir or mechanical reservoir. So, right, and there is volume exchange, but even if there is volume exchange, the amount of volume change in the reservoir, because the reservoir is so large, is negligible. So basically, the system acquires the pressure, that is pressure of the reservoir, right? So that is when you use H. So from U you get H, and again that's a Legendre transform, right? And we have seen that, and UH, and then you have G, which is where S is replaced by T and V is replaced by P, conjugate variable, and N, right? This is what we have defined here. And then there is also Helmholtz free energy, where basically you have V, but S is replaced by T. So T comma V comma N, right? So all these thermodynamic potentials we have explained, right? One is the energy, right? Another is enthalpy, right? Enthalpy is when we have a pressure reservoir or mechanical reservoir, and here it is like thermal plus mechanical reservoir. Let's call this also mechanical reservoir. Mechanical means pressure, right? So it is acquiring the pressure of the reservoir. Reservoir is the surrounding, right? And here it is basically, if we talk about this, so this is only thermal reservoir. See, here volume is basically, so pressure can change, but volume does not. So basically FTVN, when we tell, so if it's a function of T, that means the system is in contact with the thermal reservoir, right? So it acquires the temperature of the reservoir. So, but in G, it is a function of, so it is a thermal and mechanical reservoir. System is in contact with the thermal and mechanical reservoir, and thermal and mechanical reservoir means it is basically what we are specifying is temperature and pressure, right? So temperature and pressure, which are basically conjugates of entropy and volume. Now, in all these cases, you can express mu, right? So, for example, mu I equals del G del Ni Tp and J. You can also write mu I equals to del U del Ni, but in this case, this will be T will be replaced by S, P will be replaced by V, right? So, as you can see, it is SV Nj not equal to I. Similarly, del H del Ni Sp, you have S fixed, P fixed, right? Instead of V, this P fixed and N also fixed. Similarly, you can for Helmholtz free energy, it will be del F del Ni, and in this case, it is V is fixed, temperature is fixed, and Nj not equal to I, right? So, there are various ways to define the same partial molar quantity, and this partial molar quantity here that we are considering, we have been discussing so far, is the chemical potential. Now, as you know, that from Gibbs-Duhem relation that I have already discussed, at constant temperature and pressure, dG is nothing but mu1 dN1 plus mu2 dN2 plus mu j dNj, and Ni d mu I equal to 0. That is your Gibbs-Duhem equation. And this is called Euler equation at a given temperature and pressure. Right, so it is mu1 n1 plus mu2 n2 plus mu j nj. Okay, or otherwise we can also write in generally as the Euler equation is G equals to H minus Ts plus mu I, right? H minus Ts plus mu I. So if I repeats, I sometimes ignore the summation sign because the summation is already implied that I am summing over I equal to 1 to C, okay, where C is the number of components, okay. Okay, now think of mixing. What's the mixing process? What is the mixing process? When you have solute and solvent, or you have like components A and B and you are mixing it and you are forming a solution. How do you do that? Because that is what creates this partial molar quantity, like partial molar volume and so on. So basically, if you think of mixing, what you do, you basically fix a pressure, you fix a temperature, then you mix solvent A with a variable amount of solute B. Okay, because this variable amount is because, see, if you think of this, what I am telling is, how do you, if you do not have a variable amount, you don't know how to calculate the partial molar volume, right? So basically, think of an experiment where you fix pressure and temperature, then solvent A, the amount of solvent A is fixed, but you are varying the amount of solute B, and in each case, you are measuring the change in volume. Okay, so Na is fixed and Nb is varied, and then you come out. So if you have that, so basically you have data points, right? You have data points. So if I change my amount of solute amount at a given temperature and pressure, and you have a fixed mole number of solvent, then what you will see is that the volume changes as a function of Nb. Nb is the mole number of solute B, right? Now, if this volume changes, VNB, you can write it as A0 plus A1NB plus A2NB square plus A3NB cubed, right? So V0 you can write as VNB, you can write as A0 plus A1NB plus A2NB square plus A3NB cubed. So total volume V, basically what I am talking about is, what are these A0, A1, A2, A3? We are assuming that it is fitted to a polynomial of some order. Okay, here the polynomial that I am using is of order 3, right? Polynomial function of some order, right? So we are using that. So So you have V in B equals to A0 plus A1 in B plus A2 in B square plus A3 in B cube. Okay, so total volume V is fitted to a polynomial function. Now you have the step 2, that is the partial molar volume VB bar, right, which is basically del V del NB keeping NA, P and T constant, right. Now VB bar, how do you get? You already have fitted it to a polynomial A0 plus A1 in B plus A2 in B square plus A3 in B cubed, and you are basically calculating the partial molar volume, which is basically del V del NB keeping NA, P and T fixed. Okay, so it becomes A1 plus 2A2 NB plus 3A3 NB square. Okay, so you get the partial molar volume VB bar, and in step 3 you have V, which is NA VA bar plus NB VB bar. Already you know the VNB, you know also VB bar as a function of NB, right? Then basically you can get VA bar as a function from V, right, V that you have observed minus NB VB bar by NA, right. So from this equation you get VA bar, which is unknown, from VB bar, and then there is this NB, that is the amount of solute, and basically you are dividing by the amount of solvent, right, the mole number of solvent, which is fixed, which is Na. So if you have C components in a mixture, then the property Z or property Z, how do you find out? So how do you define the property Z? You have, say for example, you have C components in a mixture and you have ZK0, which is the partial molar or molar value of property Z in a, so this is partial value of property Z due to, so this is the partial molar quantity, right? The partial molar quantity is always associated with one of the components. So let us consider the component K. Okay, so ZK0 is the partial molar quantity or partial molar value of property Z in a reference or standard state of due to component K. Right? So you have component K, and think of that this partial molar value of property Z in a reference or standard state is given as ZK0 or ZK0. So if you have that, the reference state value Z0, right, Z0 is basically nothing but ZK0 NK sum K equal to 1 to C, right? So this is your, so K equal to 1 to C is a sum. So ZK0 is basically the partial molar value of property Z due to component K in the reference or standard state. Now think of this delta Z mix. What is the change? Because you have these different components, you are putting them together. So you have one component here, you have one another here, another here. So you have like one in a box. So think of this, you have like A, which contains only A component, and you have another box which is B. Then you are adding them and mixing them. Now before adding them, you had, for example, these properties like A had a property like Z, A0, and this had Z, B0. Now think of this, Z0 is nothing but ZA0 NA plus ZB0 NB. Now when you make the solution, when you mix them, then you are basically having a solution of A and B, A plus B. Now the solution is such that you may not be able to identify A and B separately, right? A and B are completely mixed together. Means you should be able to identify, means these with a very high resolution, very high resolution microscope. So in such a case, you will basically see the components A and B, right? You will see the atoms of A, atoms of B, but atoms of A and atoms of B are mixed in such a way. Say think of salt solution. You add salt to water and you mix it, and ultimately you cannot distinguish the salt and water, right? You will think that it's a clear solution of salt and water, right? So the only the physical properties have changed, but you do not basically visually see, like, unless the salt precipitates out, right, at some certain condition, you do not see whether or you cannot visually identify whether you have salt particles inside water, right? Salt particles have been thoroughly mixed in water and it has gone inside the space of the water molecules, right? Space between water molecules. So in that intermolecular space, the salt particles have already lodged and they have dissociated, into ions. You have Na plus ions, you have Cl minus ions, you have H plus ions, you have OH minus ions, right? So you cannot distinguish. So this is the A plus B solution state, right? There's a solution state. Now in the solution state, in the AB solution, right? This is called AB solution. In that you may have a property which is said Z, okay, or Z solution. Let's call it Z solution. Now Z solution minus Z naught is the delta Z mix. That is the change in the value of property Z due to mixing. Okay. So basically, what I want to tell, if you think this way, that you have, say, components 1, 2 and 3, and initially you had, say, G10 was the energy of component 1 in the standard state before mixing, and then you had G20 and G30. These were the free energies of components 1, 2 and 3 before mixing. Now, right, components 1, 2 and 3 before mixing. So these are the standard states, like 0, 0 and 0. That's why I have put the superscript of 0. Now I have mixed them. And I am looking at G solution. Now if I know this, then basically if I know Z solution, I can measure the Gibbs free energy of the solution. Then delta G mix equal to G solution minus N1. See, you have N1 components of G10, N1 moles of G1 of N1 moles of component 1, N2 moles of component 2. So N2 G20 and N3 G30, right? So basically G10, basically if I think of that, you have per mole, you have this G10 and delta G mix is G solution. So basically if you think of this is basically molar change in molar free energy to mixing, and G solution, again you can think of like G solution is nothing but the total free energy by the total mole number. So that is the G solution. Okay, that's the molar free energy of the solution, and this is the N1 G10. G10 is the partial molar quantity of partial molar free energy of component 1 in the standard unmixed state. Okay, so that's the idea, right? So remember again that G solution can also be written as you can see here, it is basically G bar K N K or G bar I N I, and then there is repeat sum over K, right? So this G bar K is the, or you can call it mu K N K, and that is of the solution, right, after mixing. This is after mixing. So you have a state before mixing, okay, which is the PO state, G10, G20, G30 and so on, and you had a state after mixing, which is like you had G1 bar, G2 bar, G3 bar and so on, and then, or basically mu1, mu2, mu3 and so on. And if you have that, then the difference between them will basically give me the change in the free energy due to mixing, or delta G mix, or delta, in this case more generally it is like delta Z mix. So delta Z mix is basically, see again, Zk bar is the partial mobile property of K of component K in solution, right? So Zk bar, so if I write this way again, just to explain to you, is partial molar property, partial molar value of property Z associated or contribute when associated with component K in solution. On the other hand, ZK0 is basically the partial molar property of partial molar value of the property Z associated with component K in the standard state, and the standard state is often the unmixed state, so ZK0. So this is ZK bar minus ZK0, and if you think of delta Z mix of ZK bar times NK, which is basically Z solution minus ZK0 NK, which is basically Z0, right, summation. So basically what you can tell is that this difference is written as delta ZK bar, that is a change in partial molar property, okay, of component K, change in partial molar property of component K, and this property Z. This Z can be anything. It can be entropy, it can be Gibbs free energy times NK, right, and that basically gives me the delta Z mix. So delta Z mix is delta ZK bar. Delta ZK bar is nothing but this, right? Delta ZK bar is nothing but this, ZK bar minus ZK0, which is delta ZK bar, and delta ZK bar NK, the summation basically gives me delta Z mix. Okay, so here again I have formally defined it. So now if you do that, then you have delta d delta Z mix. So d delta Z mix is ZK bar dNK plus NK dzk bar, again ZK0 dNK minus NK dzk0. Now as you know that NK d delta ZK, again that comes from Gibbs duhem equation. So NK d delta ZK will be equal to 0, right, d delta ZK bar. So d delta ZK bar is basically, so basically delta ZK bar is ZK bar minus ZK0, and d delta ZK bar NK into d delta ZK bar equal to 0 comes from Gibbs duhem relation, right. So this is coming from here. So then we can write d delta Z mix is nothing but delta ZK bar dNK, right, and what we also now understood is 0 equals to NK d delta ZK bar, right. This is over K, and this is called Gibbs duhem for any property, for any molar property, right. So basically again remember, when I am writing this way, G equal to GA bar NA plus GB bar NB, or here we are writing in terms of N. Remember this will not be, this is basically the total Gibbs energy, right. This is total Gibbs energy. Okay, so from now on when I am looking at solution, I will generally use this type of a notation. G, if I write total G, then total G is basically, this is total, so this is just in joule, and then GM I write is GM solution will be per mole, right. This is energy per mole, Gibbs free energy per mole, okay, or molar quantity, so let's call it molar. And when I write G bar I or mu I, then that is basically partial molar quantity. Okay, so GM, so basically if G is mu NA plus mu BNB, then G by N, where N is NA plus NB, is nothing but GM, which is the molar free energy, which is basically mu XA plus mu BXB, where XA and XB are mole fractions. Now as you know, DG is mu A dNA plus mu B dNB, where mu B and mu A are del G, that G is again total free energy, and NA plus NB equal to N. But DGM is DG by N, which is mu A dXA plus mu B dXB, right. It is basically, DGM is nothing but mu A dxa plus mu b dxb, right? And then delta gm mix, that is the change in molar free energy of mixing, is nothing but delta mu k, which is mu k minus mu k 0 times xk, right? So delta gm mix is delta mu k xk, where xk is nk by n, right? And also you know xk d mu k equal to 0, right? Summation xk d mu k equal to 0. So dgm equal to mu a dxa plus mu b dxb, and gm, as you can see, now see we have changed. So basically remember when we did na plus nb, that was equal to n, right? But here xa plus xb equal to 1, and dxa equal to minus dxb. That means dxa plus dxb, since dxa plus dxb equal to 0, right? Dxa equal to minus dxb. So dgm equals to mu a minus dxb, right? Mu a minus dxb plus mu b dxb. So what I have done, so basically dgm is mu a dxa plus mu b dxb, and we know dxa equal to minus dxb, so I am putting here minus dxb. So this becomes mu b minus mu a into dxb. So dgm by dxb is nothing but mu b minus mu. So mu a is mu b minus dgm by dxb, and gm is mu a xa plus mu b xb. So if you can replace mu a by mu b minus dgm by dxb into xa plus mu b xb, then what you get basically is, so dgm by dxb, as you know, dgm by dxb is mu b minus mu a, right? Dgm by dxb is nothing but mu b minus mu a. So you can take out xa dgm by dxb, but you have some, see, mu b xb, and you have also mu b xa, which is xa plus xb into mu b with minus xa dgm by dxb. So basically this comes out to be, gm comes out to be mu b minus 1 minus xb dgm dxb. You can also do the same thing. So basically you can get mu b, that is the partial molar Gibbs free energy of B or chemical potential of B in the solution, in the AB solution, which is nothing but equal to the, which is related to the molar free energy of the solution, and then it is also related to 1 minus xb dgm dxb. See, there is a very nice geometrical interpretation, and also remember you can do the same by starting with the definition. Like you can start with mu b, which is del g del nb for a fixed na t and p, and then this you can write as del n gm, where n is basically n equals to na plus np, right? Del n gm del nb, okay, and keep tp na tp, and then you can do a chain rule. So basically you have del n del nb, gm times del n del nb plus n times del gm del nb, and then you can express that as in terms of xb, and you will get the same relation. You will get the same relation for mu b. Mu b is gm plus 1 minus xb dgm dxb. And remember, this relation that you have gotten, this relation that you have obtained, this particular relation that you have obtained, basically you can show this geometrically by a tangent construction. So I will show you that. So you have, so as you can see here, a little bit of rearrangement, starting with this equation, a little bit of rearrangement, okay, give me the slope dgm dxb, which is mu b minus mu a. Now what do I mean by slope? So I'll just come to that. So mu b is gm plus 1 minus xb dgm dxb. Now you have some, say, molar free energy. So gm is plotted. So as you can see here, the gm is plotted here, and you have drawn a tangent to some composition x naught. Now if you see that from this relation, mu b is gm plus 1 minus xb dgm dxb, or mu a is gm minus xb dgm dxb, right? Or you can write gm equals to, so from 2 you can write gm equals to dgm dxb into xb plus mu a. Now think of this. This is basically y. This is nothing but y, right? Gm is in the y-axis. Y equal to mx plus c, right? So y equal to mx plus c. So basically you have gm as the y-axis, and you have the slope which is dgm by dxb. You have the slope which is basically dgm by dxb at the point x0, right? You can take any point, right? You can take this point and draw a tangent like this, and you can see that this is intercept c, right? This is intercept c, as you can see here. This is intercept c. So you can also write the other way, okay, in terms of xa, okay, and basically you can, or in terms of xa, and basically you will get mu b as the intercept, right? So basically dgm by dxb, as you can see, is nothing but mu b minus mu a. So if you think of this as a slope, so mu b minus mu a by, so mu b minus mu a by, so if you think of this, okay, what is the slope of this point, then if you see dgm by dxb equal to mu b minus mu, right? Okay, and as you can see that if you want to look at this, if you want to derive the same relation, you can also think of like the points. So these are like coordinates, right? So you have this point. So if you look at this point, what is this point? This is mu a. So y is mu a and x is 0, right? Xb equal to 0. That means this is pure a, right? This point is pure a, and this point is pure b. Pure b means xb equal to 1, right? Pure a means x equal to 0. So xb is increasing from 0 to 1 this way, right? Xb is increasing from 0 to 1 this way. Now if you see that, you have 0 mu a, right? This is your, so basically this is like your xy coordinates. So x is x0, then the energy is gm0. If it is 0, then it's mu a, 1 mu b, xb gm. So if you look at that, xb gm, so it is y minus y1 by y2 minus y1 equals to x minus x1 by x2 minus x1, right? When it is gm, then it is xb, and when it is mu a, then the value of x is 0, right? So if you see, and again when it is mu b, as y2, so mu b, and then you have y1 which is mu a, then it is 1 minus 0. So as you can see, gm equals to mu b minus mu a into xb plus mu a, and mu b minus mu a is nothing but, so that means mu b minus mu a is nothing but the dgm dxb that we have already shown, which is basically mu b minus mu a by 1 minus 0, which is basically, so basically if you think of this, if you look at the slope, so if you think of the tan theta here, that is basically this. What is this? This is the intercept here. So this is the intercept here. So this part, so if you look at, if I do this way, this part, so if I draw a line like this, okay, if I draw a line like this, and I tell what is this part, this part is nothing but, this part is nothing but mu b minus mu a. And what is this line? This line, the length is 1 minus 0. 1 minus 0. So 1. So mu b minus mu a by 1 is the tan theta. Tan theta is nothing but the slope of this line, right? Slope of this line. So you can see that there is a very nice geometrical interpretation of this. The intercepts of this, the molar free energy curve or molar property curve of any type of molar property. This molar property here looks like a parabola. You can see, you can make it the opposite of a parabola. So whatever be the molar property, whatever way it is, it can be any way, it can be any type of a shape. For example, it can be something like this, okay, say for example this, and if I have to draw this, I have to use my hand. So it can be any way, like something like this. So whatever be the molar property, you can always take any point here and then you can draw the tangent to any point, and then the intercepts will basically give you the potentials. The intercepts will give you the partial molar properties. The intercepts will give you the partial molar properties, or in this case the chemical potentials, right? Partial molar properties are nothing but the chemical potentials of the different components. In a binary system, you have two components. So the left hand side gives you the left hand side intercept gives you the left hand side intercept gives you the potential or the partial molar quantity of component A, and the right hand side here gives you that of the component B, right? That right hand side intercept gives you component B, and the left hand side gives you mu A, and the slope basically is mu B minus mu A, right, by 1 minus 0 in this case, right? So basically you can see that this is nothing but this y equals to m is the slope, and this is x plus c, and c is mu A, right? Again, you can think of this the other way. If you write in terms of xa varies from right to left, right? xa goes from 0 to 1, from right to left, and in that way also if you write, you basically get mu b as the intercept, right? Mu b can be taken as an intercept, or mu a can be taken as an intercept, right? So basically if I take mu b as the intercept, for example, so gm equal to mu b, and 1 minus xb is nothing but xa, and dgm dxb, right? So basically you can write this way also. So I'll come to this type of a curve in the later stage when I discuss the model, but what I want to tell now is the partial molar properties are basically, if I look at the mixing curve, if I look at the mixing curve, or if I look at the solution, if I look at the property of a solution, again I have approximated this property using this type of a curve. You will see that there are different types of curves for GM that are possible. Okay, most of the times it can be a parabolic curve, or it is not exactly parabolic. I will show you that. But what I am trying to say is this: whether it is GM, whether it is VM, whether it is SM, you have some curve. Once you have that curve, then basically the tangent to that curve basically gives me intercepts, right? It gives me intercepts on the y-axis, and these intercepts correspond to the partial molar properties of each component, right? So in binary case, you can easily see that, right? You have a curve, right? You have a free energy curve. In the case of ternary, it will be a free energy surface. Then you will have, again, you can draw a tangent plane, and the tangent plane again will cut 3 axes, and the 3 axis, the intercepts at the 3 axis will basically give me, so because it's ternary, you have 3 components, you will give me the partial molar properties of 3 components, right? The intercepts will give you the partial molar properties of the 3 components, right? Okay. But remember, there you have 2 slopes, right? You have delta GM. So you have, say for example, because you have 3 components, you have 2 independent components. So there you will have different slopes, right? So so I'll come to that later. Okay. So we do not want to go into ternary system first. We want to give more examples of binary so that you become clearer and clearer. Now, as you can see here, dgm dxb is nothing but dgm dxa, dxa dxb, and dxa dsb is nothing but minus 1. So this becomes dgm dxb is nothing but minus dgm dxb is nothing but minus dgm dxa. Similarly, d delta gm mix dxb is minus d delta gm mix dxa. Okay, so basically if you think of that, then delta gm mix is equals to d delta gm mix. So basically, just looking at this analogy, you can write that if you can write this, then you can write it for gm0 also. So basically, if you write it for that, then you can also write it for delta gm mix, which is a change in free energy due to mixing, which is again given by d delta gm mix dxb times xb, right? Xb is your x variable, and plus mu a, and mu is the intercept, right? Now you look at, this is one very important, this is called application of Gibbs-Duhem relations. Okay, so this is applications of Gibbs-Duhem Duhem relation. Okay, so basically let us say that delta H mix, that is the enthalpy of mixing, is given by this expression. Enthalpy of mixing or change in enthalpy means basically delta H mix is basically H bar, right, minus H naught, which is again basically summation Hi bar Ni minus Hi0 and 0, right? That is basically giving you delta H. Now let us assume that delta H, now in this case we are looking at the total one, but you can think of the molar one. If I think of molar one, so if I tell this is molar enthalpy of mixing, then you can directly write it in terms of x1 and x2. x1 and x2 are mole fractions. So we are thinking of this as molar enthalpy of mixing, like molar free energy of mixing. So this is molar enthalpy of mixing, and this is a function of, so this functional form is Ax1 x2. Now Ax1 x2 means, if I tell, because x1 plus x2 equal to 1, then x1 is 1 minus x2, so I can write a into 1 minus x2 into x2, right? A into 1 minus x2 into x2 basically gives me ax2 minus x2 square. Now see, when I tell, so you, as you can see that you got this relation, right? D delta G dxb equals minus D delta G mix dxa. So this is for any property, right? This is for any property. Let us have a property B, then D delta B mix dxb equal to minus D delta B mix dx, right? So here you know this expression Ax1 x2. By the way, you can plot it. You can plot Ax1 x2 where x1 goes from 0 to 1 or x2 goes from 0 to 1, or this is like, so as you can see, this is the equation of a parabola. Ax2 minus Ax2 squared is a quadratic equation. It's an equation of a parabola. Now you see D delta H mix dx2. See, I haven't used partial. So I will come to that. I haven't used a partial derivative here. I am writing D delta me. So here everywhere you are writing D delta Gm mix dxb, right? We are just using the ordinary differential form, right? We are using the ordinary way of differentiating, right? We are not using partial derivatives. We are not using partial derivatives. We are using normal derivatives. Now, why are we doing that? Why do we use d dx instead of del x, right? Because in this case, x1 plus x2 equal to 1. So x1 and x2, x1 depends on x2 and x2 depends on, basically x1 and x2 are not independent, right? Although n1 and n2 can be varied independently, if I can vary n1 independently or n2 independently, where n1 and n2 are the mole numbers, x1 and x2 cannot be varied independently. If I change x2, x1 automatically changes, right? Because x1 plus x2 equal to 1. Right? If I change x2, x1 has to change. dx2 is nothing but minus dx1, because dx1 plus dx2 equal to 0. But in the other case, dn1 plus dn2 equal to dn. Right? So in this case, it is 0. Right? dx1 plus dx2 equal to 0. So basically, we cannot use partial derivative, that we cannot fix x1 and change x2, because every time I change x2, x1 changes. Right? If I change x2, x1 changes. Right? However, when I do n1 and n2, then I can take out some n2, I can add some n1, that is possible. But here, if I want to change x2, but by fixing x1, which is an impossible task, you cannot do this, and it is wrong, and it will give you a wrong result. So you have to find out d delta H mix dx2, which comes out from this expression. So you have this expression, and for delta H mix, so d delta H mix dx2 is a 1 minus 2x2, right? Now, if that is so, as you know, delta H mix is x1 delta H1 bar plus x2 delta H2 bar. So, d delta H mix dx2 is nothing but delta H2 bar minus delta H1 bar. So, x1 d delta H mix dx2 is basically, so it comes out from here. So, you have this relation, you have this relation, and you have this relation. So, if you have that, now you have d delta h mix dx2, you multiply with x1 because you want to find out this and this. So I am just multiplying with x1, so I multiply with x1, so x1 delta h2 bar, and this is x1 delta h2 bar minus x1 delta h1 bar. So basically delta h2 bar is delta h mix plus x1 d delta h mix dx2. So this becomes ax1 x2 plus ax1 1 minus 2x2, which becomes ax1 x1 or ax1 square. So delta h2 bar is ax1 square. Delta h2 bar is ax1 square, right? x1 square, and similarly you can find out, if you want to find out, you will find out that delta h1 bar, you proceed the same way, you will get a, so basically delta h2 bar is ax1 square and delta h1 bar will be a x2 square. Okay, so if you have that, then delta h mix, so delta h2 bar, I told you delta, so you have eliminated, right? So you got this. So basically, as you can see here, delta h2 bar minus delta h1 bar is d delta h mix delta dx2, and d delta h mix dx2 is nothing but d delta h mix dx2 is nothing but a 1 minus 2x2, right? So it is 1 minus, so, and delta h2 bar is this, so delta h1 bar will be basically delta h2 bar, right? Delta h1 bar is coming from, so delta h2 bar minus delta h1 bar, so delta h2 bar, so delta h1 bar equals to delta h2 bar minus d delta h mix, according from equation 2, we get dx2, which is basically a x1 square minus a so this is x1 square minus, so this is a 1 minus 2x2. And x2 is nothing but, so basically 1 minus 2x2, so this is a x1 square minus, so this is minus a minus 2 a, so why is it becoming so complex? I just have a look at this. If you have this, let us see this way. So you have ax1 x2, and you know this is equal to x1 delta h1 bar, which is say unknown, and you have x2 delta h2 bar, which is now known, which is basically a x1 x2 square, sorry, a x1 square x2, right? So basically delta h1 bar then is nothing but a x1 x2 minus a x1 square x2. Now you take x1 x2 common, and then you get 1 minus x1, right? With a, so this is, there is an x1 here, so this becomes, so this becomes delta h1 bar is 1 minus x1, so which is x2, so a x2 square x1. So therefore delta h1 bar equals to a x2 square, right? If you plug this in, you basically get back A x1 x2 as delta H mix. So this is how we can derive. So basically, if I know delta H mix, and if I know these relations, right, these are the relations that we are using. First relation is this one, x1 delta h1 bar plus x2 delta h2 bar is nothing but delta H mix, and another is the slope, right, d delta H mix dx2 is delta H2 bar minus delta H1 bar, right, like mu b minus mu a. So basically, if I know this, I have two equations. So this is equation number 2. So if I have two equations, then I can write the third equation, then I can do 1 plus 3, and then I get delta H2 bar is ax1 squared. Then I do, again, I just plug it in here, right, so it becomes ax1 square x2, and here it is a x1 x2, and this is x1 delta H1, so I take this minus this is this, right, so this equal to this part minus this part, right. So basically, which is now delta H2 bar we know is ax1 squared, so I put it back. So if I do that, ax1 x2 common, I get 1 minus x1, which is nothing but ax2 square x1. So delta H1 bar is ax2 square, right. Now you can also do the other way, that you know the partial molar quantity of one, you want to find the partial molar quantity of other, right, because you know Gibbs-Duhem relation, you can do that. So delta Z1 bar is nothing but, if you see, delta Z1 bar D, okay, do not mistake this. So D delta Z1 bar equals to minus x2 by x1 D delta Z2 bar, right, D delta Z2 bar. So I have taken this guy here, okay. So if I do that, then plus becomes minus, so minus x2 D delta Z2 bar, and then there is an x1 here, so I take the x1 in the denominator, right, this x1 goes to the denominator. First I take this on this side, and then I take this as the denominator, right. So now if that is so, I can now integrate. Delta Z1 bar is coming from x2 equal to 0. X2 equal to 0 means pure x1, right, it is like x. So you have this relation. Now x2 equal to 0 basically means the component 2 is basically having no concentration at all. X2 equal to 0 means pure 1, right, pure 1. So x2 equal to 0 to x2, if I do, then we can write that. So this becomes minus x2 by x1 d delta z2 bar, okay. And if I know this relation, then I can get d delta z2 bar, which is not, and also you know d delta z2 bar is d delta z2 bar dx2, right. But you have to integrate this. If I have to integrate this, I need to know this. So if I know this, if I know delta z2 bar, then I can use this integration with these limits to find delta z1 bar. That means Gibbs-Duhem integration basically gives one of the partial molar properties if the other partial molar property is known. So this is an example. So if you know delta H2 bar, which is ax1 square, then d delta H2 dx2 is a dx1 square by dx1 by dx2, right. We just, so basically it is ax1 square, so dx1 square dx1 dx2, which is nothing but minus 2x1. Now if I want to do delta H1 bar, which is again 0 to x2, right, 0 is like x2 is basically 0, which is pure component 1, and you have x2 by x1 and d delta H2 bar dx2, which is nothing but minus 2x1, right, minus 2x1, right. That's what we have found it here. So you plug it into 2x1, 2a is common, there is a minus sign, there is a minus sign here, minus becomes plus, 2a goes to common, and you have x2 dx2 into x1 by x1 you can cancel, and then you get x2 dx2, which is x2 square by 2, and you have 0 to x2, which is nothing but x2 square. So delta H1 bar comes out to be ax2 square, and you are getting it if you know delta H2 bar, right. That's the idea, okay. So another very important thing I want to tell you, for example, when you wrote for G, you wrote G equals to H minus Ts, right. Similarly, for each species, you will see the partial molar property, which is like mu k or gk bar, you can call it, is nothing but, you can show hk bar, which is again the partial molar enthalpy minus tsk bar. the idea that I have, that's it's very interesting, because as you can see, this is an extensive property, this is an extensive property, and this is basically the total property, right? G is the total property of a multi-component system, right, which is equal to total enthalpy minus T minus Ts, and again H is an extensive property, G is an extensive property, S is an extensive property. But what I am telling is, if I use the partial molar similar to molar quantity, right, in the unary solution, so partial molar quantity for each species will follow the same relation, which is Gk. So this is nothing but Gk bar. You can just write Hk bar minus T. Again, T has T. So partial molar property is associated with the extensive variable here. So Tsk bar, right? So you will get the same Gk bar is my Hk bar minus Tsk. So I will continue further about solution in the next class, and I'll also give you some examples. Okay, I'll give you some examples in the next class. So you go through this, and I'll also share the lecture notes in next week. So till week 6, I will share all the lecture notes. And thanks for listening. And if you have any question, please post it in the forum.